Transfer LNG. All right. Okay, good afternoon, everybody. Hopefully you can hear me. Yep, looks like I can. You can. All right, this afternoon, we're going to cover a couple of areas, and the first one is going to be the transfer process. A lot of what I'm going to be talking about in the transfer process is transfer of LNG on an LNG tanker at a terminal, be it loading or be it distribution. The operation, the procedures followed are essentially the same. Uh, there will be some areas that I'm going to carry over naturally into the LNG bunkering operation as well. So the things that the items that I'm going to talk about with the transfer of LNG by tanker from a terminal to a ship, there are certain procedures that are followed that will not necessarily or are not necessarily currently employed when we're doing a bunker transfer by hose, from a truck, uh, primarily from a truck. But I believe that the employment of a bunker barge and a small bunker ship, some of these procedures very well will be identical procedures. So there will be some things that are done uh, uh, in one operation that might not be done in another, but please bear with me as we go along. We're going to talk about a couple of rules that always need to be followed, and if they're kept in mind, you will find that you're not going to have any problems or any difficulties when you're doing the transfer of LNG. We're going to once again stress the importance of communication between the deliverer and the receiver, and then actually following the process itself. Okay, regardless of the transfer process, there are common procedures that should be followed, and there's two basic rules always adhere. First rule is never let fuel natural gas, okay, LNG vapor and air be present at the same time at the same space. If this is accomplished, you will never have a fire. Never going to have a fire. The second rule is if you are unable to follow rule 1, and there may be an occasion where that, then you make sure that there are no uncontrolled sources of ignition in the area. So by following these two rules, you find you are going to be in a very, very good position. I'm going to take a look at that image, Jared, if you don't mind. Thank you very much. Outstanding. Very, very good. Thank you very much. I appreciate that. Uncontrolled sources of ignition. Okay, people say, well, where the heck is this going to come from? Uncontrolled source of ignition is those not considered in the design of the facility and may not be under the direct control of the operator. Examples of this: smoking, static buildup on clothing. This is something that a lot of people don't pay much attention to, but we can build up a static charge on our clothing, and we have to be aware of this. So usually the clothing that's worn on board a vessel for the people involved in the cargo transfer of LNG are of such a material that you're not going to build up this static discharge. Dropped objects. You have to be very careful about this. Most of the tools that are used are non-sparking tools. Actually, all of them should be non-sparking tools, so that if a tool is dropped and it hits metal on metal, you're not going to get a spark. And the use of non-approved portable electrical equipment. That's why I stressed radios have to be intrinsically safe. Any other type of electrical equipment in the vicinity of a gas operation has to be gas tight, intrinsically safe, so that there's no chance of generating a static charge or an electrical charge that could be a source of ignition should there be an area where there are LNG vapors in the environment, in that critical mixture of range of 5 to 15% by volume and air. Each operator, again, we're being very, very repetitive, but these are the things that are important and have to be adhered to at all. Each operator must have a intrinsically safe UHF walkie-talkie and a direct phone line, and have the ability to view levels, temperatures, and pressures of their tanks at all times. So if you go into the cargo control room of an LNG carrier when the transfer of LNG is taking place, you'll find in most cases there's going to be 3 means of communication. One of them is going to be a walkie-talkie. The other is going to be what's called a hotline. That's a direct phone line directly from the CCR of the control room, the cargo control room, to the cargo control room of the terminal. It's a dedicated phone line that is used for nothing else. It's a good analogy would be with the hotline of the President of the United States, the President of China, uh, uh, former Soviet Union, Russia, where the world leaders get in contact at a moment's notice and directly to each other without uh, any no intervening issues or control points. So this direct phone line is there, and then there's also a normal phone line. And in today's society, we also have the ability to use cell phones as well. So you have these various means of communication that are available for the operators in both the ship's control room and in the terminal room. Uh, on board the ship in the control room, obviously there's control consoles, and on those consoles you're going to have screens where you're going to have your tank levels, tank temperatures, tank pressures, temperatures at various points in the LNG system throughout the ship, as well as the vapor side of the system throughout the ship. These things can be monitored at all times. For the LNG bunker transfer communications, again, each operator must have the ability to monitor temperature and pressure, the ability to monitor alarms, and the ability to activate emergency shutdowns. The standard transfer procedure is hard arms or cryogenic hoses. Cryogenic hoses are used on board LNG carriers primarily in ship-to-ship transfers of LNG. In the early years of the LNG trade, uh, ship-to-ship transfer was a highly unusual event. Matter of fact, if you had a chance to look at the safety record and ship casualties over the years, see that there is one in there that occurred in October of 1980 involving a vessel called the LNG Libra. And I was chief officer on board that ship at that particular time. And we were sailing from Indonesia to Japan with fully loaded cargo, and we were off the southern tip of the Philippines, off of the island of Mindanao, and we suffered a casualty on board the ship where our tail shaft actually broke, and we lost the ability to propel the ship through water. And as a consequence, we were towed into protected waters of the Philippines, and we conducted a ship-to-ship transfer from one of our ships to one of our sister ships. And this was only the second time in the history of the LNG trade that a ship-to-ship transfer was conducted. And believe me, at the time, this was a very, very big deal. First time was I believe in 1979, it involved a vessel, an LNG carrier that went aground in the Straits of Gibraltar fully loaded, and was subsequently, the cargo was subsequently transferred to another vessel. But what was interesting about it is this is something that had rarely been done, and it was conducted completely in a safe manner, and that cargo eventually made its way to Japan, and we eventually made our way to a shipyard in Singapore where repairs were effected. We were returned to service. So hoses are commonly used today. Ship-to-ship transfers have become a relatively common experience or a relatively common event in the LNG trade today. Several hundred of these transfers have been conducted on a routine basis, and flexible cryogenic hoses are used for particular type transfers. At terminals, though, you're going to find that there's going to be a hard arm connection between the supply and, for a ship going into a terminal, the supply source is the ashore tank. Vessels going into a bunkering operation, The supply source could be a shore tank, and the loading process could be through a hard arm. It also could be through flexible hoses. Your other supply sources could be a barge, a bunker ship, a tanker truck, or the use of the cassette tank system. That's the stacking, uh, those C-type C-tainer systems where the uh, containers are locked in and they contain a vessel that contains the LNG under pressure. Regardless of the transfer modality, there's certain procedures that are common to all. The first one is obviously, and we've talked about this on numerous occasions, is the establishment of a safe zone, a security zone. First of all, around the vessel, around the terminal, wherever this operation is taking place, and you're also going to have a security zone. The first operation that occurs is going to be the connection of the hard arms, the connection of the hose. Okay, where we're using hard arms, the next step is called the purging of the hard arm. When that hard arm is connected to the vessel, it contains oxygen. It may contain a little bit of methane gas. So what happens is that arm will be purged with nitrogen. Nitrogen will be supplied from the shore supply. Usually, if it's a terminal, it's going to be from the nitrogen supply of the shore terminal, and the nitrogen is put into the hard arm under pressure, and then is bled off until you have less than 1% oxygen, and the remainder of what's in that pipeline is now nitrogen. So you have this inert environment that you're working with. This is after the connection takes place, before the actual cargo operation starts. Uh, Following the purging, we go through a series of tests. We're going to do we've done our communications test, and we're going to check the alignment of our system and whatnot. And we're going to do what's called a cool down operation. The hard arm is going to be at ambient temperature. Ship's piping up to the manifold valves, the control valves on the ship's manifold where the connection takes place. That ship's piping is already going to be cooled down by the ship. It's been done as the ship makes its approach to the terminal or the berth. In most cases, some terminals maybe or some ports don't allow this, so you may have to wait until you're alongside at the terminal before that cool down process starts, and then it would be done in conjunction with cooling down the arms. But there's a period of time where everything that's going to be used in the transfer process has to be cooled down to cryogenic temperatures. So this is done in a controlled manner. Following the cool down, the ESD system is going to be tested, and this is done both from the ship and from the shore. Control valves are placed into the open position. The ESD is activated to make sure that all valves that are supposed to close. Anything that's supposed to remain open remains open. And once that's ascertained that it works from the first initiator, usually will be the ship, everything will be reset, and then the system will be tested from the shore side control to make sure their controls are working. Then the actual transfer of LNG, whether it's an LNG cargo or whether it's an LNG bunkering operation, will take place. If it's a bunkering operation, it's going to be of comparatively short duration, let's put it that way, when compared to transferring a cargo. A cargo transfer for a vessel that's cold and ready to load condition usually takes from the actual transfer takes 12 to 14 hours. An LNG bunkering operation, because of the quantities involved, is going to take considerably less time, probably several hours. Following the transfer operation, we then go into what's called a gas freeing operation, where the hard arms or the hoses are going to be purged of liquid. And this is usually done by introducing nitrogen into the piping system, forcing any residual that's left over in the arms or in the hoses into the cargo tanks of the ship, uh, and then eventually getting those hoses or hard arms to a point where the environment inside those pipelines is virtually 100% nitrogen. Uh, Following that, we have to de-ice. As if you did watch that video last night of the LNG tanker, you could see that during the actual operation, there's a buildup of ice on these arms. There's a buildup of ice on piping. There will be a buildup of ice on the hoses, and depending upon where the operation is being conducted, if it happens to be in an area that is where there's high humidity, that ice buildup can become considerable. You can have several centimeters of ice, several inches of ice buildup, and before anything gets disconnected, you have to de-ice, and this de-icing is accomplished by using seawater, spray seawater onto these various items until the ice is gone and safely handled. Uh, then you do a disconnection. The disconnection process is a very, very methodical process, and usually in conjunction with the disconnection, the custody transfer, the measurement of the volume of cargo transfer is conducted on board the ship, and the ship's figures are used as the quantity of LNG, the official quantity of LNG that has been transferred between the deliverer and the receiver, terminal, or the vessel, whatever the case may be. So we're going to set up this safety zone. We've talked about this before, and we may probably mention it again. But what we're going to do is we keep all personnel not directly involved with the bunkering operation away from the bunker manifold area. In the case of the bunkering operation, away from the manifold area if it's a cargo transfer operation. And those personnel are kept from any potential exposure to vapor or escaped liquid. Very rare occasions where you're going to have a vapor or a liquid escape, but you're always aware of this. Dealing with a cryogenic liquid at minus 160 degrees, and the consequences of exposure to cold vapor or to liquid is serious, and serious burns can result. You get an actual burn very, very similar to a burn from heat. So therefore, it's also important that the people involved in this operation, when they are in these areas of the operation, that they are wearing the appropriate personnel protective equipment. Anytime you're handling valves or working in close, you want to wear protective clothing, protective gloves, face shields, things of that nature are the typical PPE that's employed during the transfer of LNG cargo. So we're going to do this connection of the hoses arms to the ship's manifold or to the bunker manifold. One of the first things that's done before we actually make this connection is we are going to inspect the flange faces. You've got a hose flange or an arm flange that's going to be mated to a flange on the manifold. So you want to inspect the flanges to make sure there's no defects, cuts or gouges or scrapes, because these types of things can lead to a leak. Flanges are usually clean. Mating surfaces are clean. The ship's crew or the terminal staff, they'll use rags. Not using a cleaning material, but you make sure the face of these flanges is in good condition. Then there's going to be a gasket or an O-ring installed between the flanges, depending upon the type of flange. Some flanges are so constructed that they use a gasket. Other flanges are so constructed that they use a series of O-rings for the sealing surface of the flanges. In either case, these gaskets are always renewed each time a transfer is conducted. Uh, O-rings don't necessarily have to be renewed, but they do have to be inspected to make sure that the O-ring surfaces are intact. Uh, Oftentimes, my experience has been working in terminals. Uh, Usually there's a series of 3 O-rings that make up this sealing surface, and because of the way the surfaces are mated, usually one O-ring seems to take a beating, and you have to keep a close eye. Usually it's the middle O-ring of the 3. And that O-ring, for some reason, is exposed to more stresses, and it's the one that is usually going to give you a problem. So that middle O-ring, you have to pay very, very close attention, and oftentimes that's the one that has to be replaced. It's always it's incumbent upon the terminal. Usually, the terminal supplies the O-rings on their arms, and if it's a gasket operation, usually the ship is responsible for having a supply of gaskets on board the ship. This is something that usually will get covered and discussed at the pre-transfer meeting during the signing of the declaration of inspection or declaration of safety and whatnot. Who is going to provide what? Just as an aside, in section 311, when we were talking about the checklist, those hyperlinks that are in the PPT, you cut and paste that hyperlink into your browser, that will take you to the sites where you can actually take a look at those various safety lists that we covered earlier this morning. So if you're interested in getting a little bit more detail on those, to see exactly what's contained in the 4 or 5 parts of that particular safety list for the various modalities of LNG transfer, they are available if you use those hyperlinks. Flanges, we have the insulated flanges that are going to be used. That's per SIGTO best practices. ISCOT is another body that comes up with guidelines, as well as ISO. Traditionally with arms, a leak test, once the connection is made, the gaskets are in place and the connection is made. Now this connection can be made either with bolted flanges with a series of bolts that connect the flange, or a hydraulic device which is called a cam lock. It's an automatic locking device that's operated hydraulically. It doesn't make any difference which type of system is used. They're equally effective. The cam lock operation is a little bit faster than the bolting, and actually because you're controlling these locks hydraulically, there's usually equal force on these cams, and you're actually less likely to leak using cam locks than you are with bolts, because when you bolt up, there's usually 12 to 16 bolts. Sometimes the forces used in bolting up can be uneven, and you have a tendency to have some minor leaks or first starting your operation up. But in any event, prior to once the arms are connected, nitrogen is put into those arms to purge any methane from them, and then the pressure is allowed to build up in your liquid arms to approximately 5 bar. Once that pressure is attained, a soapy solution is usually spread around the flange connection, and you just observe it. If there's a leak, you're going to get soap bubbles, and if there's a leak, obviously take measures to stop that happening. So you're testing the system before you're introducing any LNG into it to make sure that it's tight as possible to be. The vapor line is the vapor arm is similarly tested, but it's tested at a lower pressure, 1 to 2 bar. Same procedure is used. Soapy solution, products on the market. I think one of the more common ones is a product called Snoop, which just bubbles very, very much if there's a leak, if it's exposed to leak. So Soap and water is just as effective, but it's just the important thing is that these connections are tested to make sure that the possibility of a leak as much as possible. Again, the soap tests all connections, and soap will bubble if there is a leak. Next, purging is part of this entire process, and what we're going to do is we want to make sure that there is no oxygen remaining in the arm. And again, this is done with nitrogen. You keep continuously pressurizing and releasing the pressure with nitrogen, which is normally supplied by the terminal. This also can be supplied by the ship if necessary, or the ship can also supplement. The endpoints of a purging operation is an oxygen content with an oxygen meter of less than 1% by volume. A lot of terminals, and I know ships will normally do this routinely. Not all terminals require it, but most ships are also going to check the dew point of the environment that's in that pipeline. And what we want to see is the dew point of less than minus 40 degrees. Not that should be less than minus 40 degrees centigrade. That way we're certain that the environment is dry and that the possibility of the formation of any ice particle is eliminated. Ice is not a friend of LNG pumps, so obviously you do not want any moisture in the system. There is no water content in LNG, but you can pick up moisture in your piping systems of the terminals, the hoses, etc. So always make sure that there's no moisture in those transfer systems, and that's checked with a piece of equipment called a dew point meter. Again, minus 40 degrees is the target that we're looking at. Following this operation, we are now going to commence the cool down of the transfer system. As I said, the vessel in most cases is going to have its piping cooled down to the ship's manifold, and the terminal will be cooled down to the base of the loading arms or to the manifold from which the transfer hose is connected. But you now have this loading arm, or you have a hose that's still at ambient temperature. So, if we're down in Singapore, we're looking at, this is at 33 degrees, plus 33, 35 degrees centigrade. And before we can do the transfer, we have to bring that pipeline or that hose down to at least minus 130 degrees centigrade before we can enter liquid. So this is done initially by allowing cold vapor to enter the piping system, and the cold vapor begins to cool this down. As that temperature begins to increase, we can begin to introduce a very, very small quantity of LNG into it, and this progressively decreases temperature. So once we get down to minus 130 degrees, we are in a position to begin the transfer, or we're in a position to now put LNG in quantity into the pipeline, into the loading arm, into the hose. The contraction of that hose, the nearly 100% of it has already been completed at minus 130 degrees. So at that point, we can now introduce LNG into it safely. So the cold methane gas cools down the line until it's replaced by LNG. And once we reach that point, we are now at the point where we are going to test our emergency shutdowns. This is the typical procedure. It can be done. The testing of the ESD system can be done with a warm system, or it can be done with a cold system. My preference has always been to do a cold test, because that's the operating conditions of the system. Some terminals, they like to do a warm test. Either one works. The important thing is that the system gets tested and that valves close when they're supposed to close. So we're going to test it, and usually it's done first from the ship to the shore. Uh, all of your control valves that are supposed to be open are open. Pumps are shut down, so there's no product flowing at this point in time. The system basically is static, but it is cold and it is full of LNG. Uh, so the ship will initiate a trip. Usually it's going to do a countdown with the shore. Communications done over the radio. Shore control, ship control to shore control. We're going to do the EST, counting down 3, 2, 1, trip. As soon as you hit, you trip. The ship knows immediately that the trip has been activated. The shore is going to respond, we've received the trip, we're shutting down. Once all valves that are supposed to close are closed, each side acknowledges that their system is closed and that they're going to reset the system. ESD system is reset, so it's put back into its active state, and valves are reopened. And we now do the same procedure, except in this case, the shore is going to initiate the trip, and the same thing happens. They're going to do a countdown, they give a notification, they do a countdown, trip, shore acknowledges, ship acknowledges that they've received the trip. Once all valves that are supposed to close are closed, each side acknowledges that their system is in a shutdown state, and we once again reset the system, put it into its active state. The next step is to actually start the transfer. So we have our loading arms are full of LNG, or hoses are full of LNG, and we're all set to start this procedure off. We start it off slowly. We'll start one pump if it's a transfer at a terminal, and that pump is usually started at a reduced capacity. Do this because we want to first of all ascertain the tightness of our system. So we begin everything in a reduced mode. System is being constantly checked by ship's personnel. We have crew members who will be out observing the transfer system as we begin the cargo transfer. We continue starting pumps in a sequential order, usually over a period of anywhere from 3 to 6 minutes between each pump start. Once all pumps are operating, then we begin to what's called ramp up or rate up the pumps to their maximum transfer rate, the transfer rate that was agreed upon by the terminal and the vessel. During this ramp-up period, again, your transfer system is going to be checked and monitored by personnel. And during that period of time as well, temperatures, pressures, and levels are going to be monitored by personnel in the cargo control room of both the terminal and the vessel. Once you reach your maximum agreed upon transfer rate, you're at steady state at that point in time. And essentially what occurs now is just simply the monitoring of the system, watching temperatures, watching pressures, watching tank levels. And again, during the entire process, on board an LNG carrier, the entire cargo system is always going to be maintained by personnel. There's always going to be someone from the ship's crew out making constant rounds throughout the system, just to make sure that everything everything is tight, no problems, and there's no leaks of any type. Once we get to the point where we're going to start topping off tanks, topping off tanks is bringing the tanks up to their desired full level. We begin to reduce the transfer rate of the pumps, and that's done by reducing power to the pumps, electrical power, reducing the volume of liquid that's being pushed through that pump. That process is called ramping down. So we ramp down in a progressive, orderly manner, so that we don't, let's say we're on a ship that has 5 cargo tanks, we don't wind up reaching the full level of each tank at the same time. We want to stagger tank levels, and we want to bring tanks up one at a time so that we can start securing pumps, start slowing this process down so that when we get to this last tank, we're usually operating on one pump at a reduced capacity, and then we can wrap the operation up in an orderly fashion. Uh, in a bunkering operation, it may only be one pump operating, or it may be a pressure transfer. Again, if it's a pressure transfer, the flow can be controlled by throttling in on a supply valve, so that once again, when that tank is being brought up to its full level capacity, it's done in a controlled manner and can shut down without causing any problems, any pressure surges in the system. So this is the topping off procedure. I think I already covered that. And once we're topped off, we complete the transfer, stopping the pumps, closing the valves. Following the actual transfer process, again, this is a ship at a terminal. We're going to have to gas free the loading arms. So we now have these loading arms that are full of LNG, and this LNG remaining in the hoses has to be displaced. So what are we going to do with this? Well, again, we go back and we're going to use the nitrogen from the shore supply, or if necessary, it can be used also from ship via hose over to the terminal if for some reason they have a shortage of nitrogen. And the valves, the block valves at the base of the arms are closed. And what we do now is we introduce nitrogen under pressure into the arm, and then through a bypass valve, we lead the remaining LNG that's in those arms, force it under pressure into the cargo tanks of the ship or into the bunker tank of the ship. This is done in a controlled manner. This is one of the reasons why when we top off, we're also going to allow a certain amount of area inside that tank for the little bit of liquid that remains in these arms. When you're talking loading arms, you're probably looking upwards of 50 to 75 additional cubic meters of liquid that's going to be put back into your tanks when you do this gas freeing operation. So this has to be taken into account. If it's a bunkering operation, obviously that amount is probably considerably less, but this is something that can be discussed in the pre-discharge or the pre-transfer meeting with the supplier. You know, what's going to be the volume of that hose when we finish, if we're going to do a gas freeing of the hose prior to the disconnection. So we have to take this into account when we're calculating how much liquid we're going to put into this tank during the transfer process. So we put these arms under pressure, nitrogen, and we displace the LNG to the ship, or it could be actually returned to the supplier's storage tanks. If it's a tanker truck and we're operating on a pressure discharges, the pressures that are going to be developed during a gas freeing operation are not great enough to force this back into the tanker truck, so it will go into the ship's bunker tank. If we are in fact conducting this gas freeing operation, the end point of that is we're going to test this with one of the ship's meters, one of the ship's gas meters, and we want to see a gas concentration of less than 1% methane by volume. Even though the LEL of methane is 5%, we have a safety factor in there that's pretty internationally adapted. And almost every vessel that I have ever been on or worked on or terminal is the end point of that is going to be less than 1% methane. This way you know you are in a safe area. And also the little bit of methane that's going to be released when you actually connect now at a minimal level. Getting down to 0% methane is it is something that usually is not attained, mainly because of the time involved, the amount of nitrogen involved down to down level. So usually, uh, most acceptable, widely acceptable endpoint limit is 1% of methane by volume. Following this, or actually it's done in conjunction usually, is you begin de-icing your loading arms. And the actual de-icing of the loading arms is basically that area that is based around the flanges. This is what you're mainly interested in. The loading arms are very, very large devices. And if you've watched any of the videos, you see that the de-icing of a total arm would be extremely time, really of very, very little value. So what you really are going to just de-ice the area within a meter or so of the flange. And again, this is usually done with water spray uh, supplied by the ship, and the water is just sprayed on the icing area until the flange bolted connection is exposed and you can get the bolts, or that the cam lock arrangement are free of ice and can be operated in hydraulic pressure in the cam locks. So you get all of the ice off, you can now begin your disconnection. It should be iced. So once your gas-free and de-ice hoses arms are disconnected and returned to their stowed location or stowed position. The arms are then retracted into their stowed position as I've indicated, and the blinds or blanks are placed on the manifolds of the vessel, and we then proceed to the post-discharge meeting, which is always going to be conducted between the terminal and the vessel, or between the vessel and the bunker supplier. Going to go through a checklist, make sure everything that is secured has been properly secured. Custody transfer is going to be conducted. And this is an operation that is normally done once all of the liquid is out of the loading arms. Once it's determined that all of the liquid is out of the loading arms, or once the liquid is out of the hose. This is usually done during the gas freeing part of the operation, where the methane gas is being purged out of the arm or out of the hoses, if in fact it is being done with the hoses. So it's done in tandem. A lot of these operations do overlap and are conducted at the same time. So we're going to do the custody transfer with the gauging equipment, where the quantity of LNG bunkers transferred is determined by a mutually agreed upon method between the bunker supplier and receiver. And the two most common methods that we've gone over is the volume determined by calculations from the vessel tank level system, and it also can be done by flow meter. I have not had much experience with flow meters, but I do suspect in bunkering operations this may be a little bit is going to be more common than with a terminal operation, transfer of cargo from a terminal to a ship. But usually the calculations of the vessel's tank level system are the figures that are going to be used. This is the system that's certified by customs, and this obviously makes it a critical component to determining the volume that's been transferred. It's been approved by customs, ones that use for the assessing duties, the assessing levies, taxes, etc. So consequently, it's the one that's most accurate, and this is the one that is most commonly used. Regardless of the method used, the volume transferred to be agreed upon by both. Some terminals or some companies, they will use an independent surveyor. So the ship will have its figures that it's used from the custody transfer system, but the independent surveyor will also use his own figures. He uses the gauging tables, whatever the case may be. Uh, Usually his method of determining it is independent of the actual gauging system. And when he reaches his final numbers and final figures, they're compared with the numbers and figures that the ship has determined. And in most cases, these agree, usually out to the second or third decimal point. So it's not an issue using an independent surveyor. But some companies like to have that independent surveyor there who certifies the volume that's been transferred. Uh, Following this, we now have the documentation signing by both parties and the after LNG transfer checklist. As I just mentioned a short time ago, if you go to you take those hyperlinks out of section 3.11, load them into your browser, you can access those checklists and you'll see the items that are covered on the post-transfer checklist. Uh, Once that is accomplished, everyone usually tends to shake hands and say, have a very nice voyage, and they depart the vessel, and the vessel departs the terminal. Uh, at every step of the LNG bunker transfer, please remember safety first, last, and always safety first. Again, I cannot emphasize safety, something such an integral part of the operation. Important, everybody becomes a member of the culture. Transfer process again is based on those very, very two important first rules, not letting air and gas into. If you follow this rule, you're not going to have a problem. You're not going to have any. And making sure that if you cannot follow rule one, that if air and gas are going to mix, that there's a source that's going to go in the trouble. The operation is very, very specific, and if carried out in the way it's laid out, uh, these operations will be conducted uh, without incident, uh, to the point where I hate to say it, they do become routine, but that's something you always have to be on guard of. Complacency is always an issue. So what you try to do is we try to conduct these operations as the first time. We always have to walk into it with that particular attitude. We're looking at it as okay, we've never done this before, and this is how it's going to be done. You're not going to miss anything. And unfortunately, that's where complacency places us. If we begin to think that we know it all or we've got this all memorized, uh, you find that this is where accidents occur. So we have to pay very, very close attention to steps, regardless of how many hundreds of times it may have been. Above all is safety, safety. Right? All right. I pulled this to a halt a little bit sooner than I thought I was going to, Jared. Uh, I believe as we go along this section, we're going to have a picture of a loading arm arrangement with emergency release couplings and whatnot. I'm not going to try to go into that right now. What I can do, if it's okay with you, I'm just going to jump into I'll jump into the next section, and we'll go until the 1500 break, and then come back and wrap things up. If that's okay with you. Right. Uh, registered. Okay, Kelvin, you have asked a question. Using marine gas oil, marine diesel oil, and intermediate fuel oils bunkering operations. A document that gets signed at the end is called the bunkering delivery receipt. And often the quantity is expressed in metric tons. Is the same thing true for LNG bunkering? The standard unit of measurement in LNG is going to be cubic meters of LNG, okay? And the certificate of volume and measurement, which is the document that's generated by the custody transfer system, uh, that is going to that will indicate that what the volume transferred was, and that volume is in meter cubed, m cubed. Okay. All right. If everybody's ready, we're getting into a little bit more exciting area, I guess, at the moment, and something that I'm sure has been in the back of everybody's mind. You know, we're talking about keeping LNG vapors, gaseous natural gas vapors, out of air. We want to always make sure that we're out of that 5 to 15% area if, in fact, the natural gas does get into air. Exactly what happens, and what we're going to jump into here, and we'll do this for the next half hour, is LNG fire. Uh, if you are involved with a port authority or a terminal operation, shipboard operation, you will, and probably in all cases, you're going to receive various firefighting training. Firefighting training is required by the shipboard people, required of the shipboard people by STCW requirements. All seamen have to go through a basic firefighting course, and most everybody also goes on to advanced firefighting courses and firefighting techniques. In addition to that, if you're going to be involved in LNG operations, and most likely you will also be required to take a course that's going to involve the actual exposure to fighting fires involving natural gas and other gases, propane, ethane, ethane, things of that nature. So you will be taking courses in that if you haven't at some point in time. We're going to look at the basic elements and types of fires. We'll once again take a look at the vapor dispersion, jet fires, pool fires, the typical types of fires, and also a phenomena that is called rapid phase transition. The elements of fire, the basic elements, as we go into these advanced courses in firefighting, we've kind of gotten away from the old basic triangle, 3 things required for fire. But for the purposes of this course, we're going to look at the 3 basic items that are required for a fire. First of all, you have to have a source of fuel. Without the fuel, you're not going to have a fire. You have to have air, and you have to have a source of ignition. Any one of these 3 items is missing, you're not, in almost all cases, you will not have fire. So we'll follow follow the first commandment of handling LNG. Thou shalt not allow sea or the mix with oxygen, goal, and something that we try to attain at all. But we also have to be prepared if this doesn't happen. So key points to remember, methane is like any other hydrocarbon. It's flammable. That's, it's a cryogenic liquid or a liquefied natural gas, methane in its liquid state. It's a cryogenic liquid. It's a cold hydrocarbon. And like all hydrocarbons, regardless of where it is, what it is a flammable product and it can burn. The flammable range, once again, we stress this, and please remember this, is going to be 5 to 15% methane by volume in air. Consequently, LNG does not burn. It's too rich. So the LNG itself does not burn. It has to vaporize. You have this phenomenon called boil off. The surface area above the LNG is warmer than the LNG. So the liquid is going to boil, and this is the area where you can get your flammable vapors should it be introduced into air. But the LNG itself does not burn. It's like gasoline. Gasoline does not burn. It's the vapors that burn, and it's the vapors that are within that 5 to 15% volume by air area that are going to burn. Anything outside of that area that's too rich, above 15% by volume, it's too rich, it cannot burn, and anything below that 5% is too lean, it cannot burn. It's only within that range. LNG does not explode, but LNG vapor does burn, and LNG vapor will explode if it's in an enclosed space, if it's in the proper concentration, and if there's air. Again, you have to have air, you have to have a. So any of these explosions that we read about in the newspaper, natural gas explosion in an apartment building, in any type of building, what has happened there is obviously there's a leak, proper concentration of gas was attained, that 5 to 15% range. Somebody flicked a light switch, somebody lit the stove, they lit a cigarette, something of that nature. And if they are within that area where we have the 5 to 15% range, and it's a confined space, you will have an explosion. But it's the vapor that explodes, not the LNG. It's the vapor that burns, not the LNG. The various types of LNG fire. You have a flash fire, what's called a flash fire, or a vapor cloud fire, jet fire, pool fire. Uh, the next one is called a BLEVE, and this is more common with propane and butane in large propane and butane tanks. But with the advent of the transport of LNG and tanker trucks, it's also something that could happen with natural gas. And we will see a short video of a BLEVE and see what actually happens. And I will explain what a BLEVE is as into the section of the presentation. And then we have a phenomena which is called rapid phase transition. We cover this under the fire area. Rapid phase transition is not a fire, but it is a phenomena that LNG that can be seen with LNG. As a matter of fact, believe in this little video that we have. Yes, okay. If you watch this little video at the base of the PPT, what you see here is a LNG pool fire. There's actually LNG in that pit, and what they're doing is they're spraying in water at a very, very high volume. And what happens right here is that water actually hits the liquefied natural gas. And when it does that, the liquid absorbs the heat from the water and vaporizes very, very rapidly. You get this concussion. In not an explosion. It's not a fire. There happens to be a fire in this video, but that explosion that you see there is rapid phase transition, and that added the volume of vapor to the fire. Obviously, intensifies the fire. I believe we'll have another picture of rapid phase transition a little bit further on in the presentation. I have a question here that I'm looking at, gang. So let me. Whoop. Traditional mariners use oil fuels who are now asked to may not be balanced. Okay. Yes, Jerry, that's a good. Yeah, that's a good question. Uh, uh, yeah, let me mull on that for a second, and perhaps before I get to the end here, before 3 o'clock, we'll put that a couple of discuss. Yeah, but it is a very, very good question. All right. First type of fire is a flash fire or a vapor cloud fire, and this is something that may occur. Cloud of gas burns without generating significant pressure. In other words, it's an unconfined vapor. And that cloud obviously has to contain the 5% to 15 concentration of methane in air and meet a source of ignition. And if it does meet a source of ignition, you do get a fire. But the only thing that burns, this is very, very interesting. The only area that's going to be burning is where that concentration is 5 to 15%. Anywhere outside that 5%, 15% area is not going to be involved in flame. So the fire will burn back to the source. There's an LNG leak, and get one of these flash fires or vapor cloud fires. Fire will ignite, and you'll see this in one of the pictures further along. The flame will propagate back towards the source, but it's only going to come back back to the point where that 15% concentration of vapor is located. There's going to be a distance between that and the actual source where the concentration is going to be too rich to support a flame. An analogy would be is a butane cigarette lighter. If you light a butane cigarette lighter and you take a look at the flame, there's an area between the actual tip of the nozzle and the flame itself, fire. And that area, the concentration of butane is too rich to burn. So you have the same phenomena that occurs in one flash fire or a vapor cloud fire. These are not common things, but these are things that can happen. Just as a reminder, we'll take a look at the vapor dispersion diagram. This is your vapor cloud. At point A, you have your source of the spill. Initially, the vapor is going to be in this area, area B, and that concentration is going to be too rich to support combustion. But as that cloud disperses, it's being moved by the wind direction. The wind is coming from right to left, and that cloud begins to disperse. And as it disperses, the mixture of or the quantity of methane in air becomes diluted by the air. Eventually, it's going to reach the point right here where it's 15% methane by volume in air out to the edge of this vapor cloud where it's now 5% at this point. Anything outside this point is too lean. So if Joe Mariner is standing here and decides he's going to light a cigarette and he lights it here, nothing's going to happen. But he better not be standing in here when he decides to light his That's why we have designated smoking areas on ship. Folks still decide they would like to smoke. Uh, just in case. Uh, we don't walk around on LNG carriers or on LNG bunkering operations with vapor all over the place. It just doesn't happen. Systems are entirely closed systems. They're designed to be closed. They operate totally closed, and it's certainly an unusual occurrence. It's an anomaly when we do get any amount of methane into the environment. But this is just so that you're aware of what potentially can happen, and uh, and if this does happen, if a fire does occur, how that fire is going to propagate. That fire would start here, and it would begin to work its way back, and it's going to work its way back until it reaches a point where the concentration is too rich to burn. So there would be no, in this particular example, there would be no flame in this area, but it would be flaming all the way up to it. Uh, what's occurring here, though, is something that you have to bear in mind, is that as this flame works its way back, it's generating heat, and that heat is going to vaporize any liquid in here more quickly. So in a scenario here, and a lot of tests have been done. Sandia Labs in the United States has done numerous testing. They've done numerous testing in France, and they have a very, very good idea of what would happen in the occurrence where there was a massive failure and there was an LNG fire on board a ship. And it's been pretty well determined that you're going to find yourself in a situation where you're going to have one huge fire is what you're going to have. Uh, chances of explosion are remote. Uh, there have been occurrences where LNG ships have been struck by rocket-propelled grenades in war zones and whatnot, and have experienced fire, but there's never been an explosion, to the best of my knowledge. There was a video that was available several years ago. I wish I had it because it's a very, very interesting video, and it involved I believe it's mentioned in the safety review done by CH4. It was a propane or butane carrier under Japanese registry where there was a collision. They had a couple of outboard tanks that carried a highly volatile, I believe it was benzene, something like that. So when the collision occurred, immediately there was fire on board this on board this LPG tanker, and this happened in Tokyo Bay, if memory serves me correctly. And uh, they couldn't put the fire out, so the Japanese authorities decided the best course of action would be to tow this vessel out to sea and sink it. So they did do this. They managed to tow the vessel out to sea. It was attacked over a period of several days by the Japanese Air Defense Force. They shot rockets into this thing. They did everything in their power to blow this vessel up and sink it, and it was almost they couldn't blow it up. They couldn't blow it up. Eventually, the thing burned to a point where it sank, but the idea that the LNG carrier is this massive bomb that's going to explode if there's an unfortunate incident, we have a collision and a resultant fire. Uh, chances are very, very small. Uh, of course, the ideal is never get yourself into that position. The way ships are operated, with their safety zones around them, their security zones around them, chances of collision are greatly reduced. But this is always a possibility, particularly talking vessels operating in very busy ports or very, very congested waters. So it's just be aware that these vessels are extremely safe, and the nature of the cargo is such the chances of actually experiencing an explosion are very, very remote. Okay, if we have this vapor cloud fire or flash fire, The cloud's going to be ignited at the edge as it disperses and meets the source. Ignition sources include open flames, sparks, internal combustions, and once ignited, the cloud will flash back along the flammable range of the vapor cloud. Uh, Internal combustion engines is one of those sources that oftentimes don't get taken into consideration, uh, particularly in a terminal operation. We have all sorts of vehicles uh, transiting and riding around. Uh, Very much aware of this issue within a refinery, for instance. And even in refineries, unfortunately, over the years, there have been instances where personnel have gone into an area where they had a vapor cloud of some type, uh, have failed to turn off the engine of their vehicle when they've approached it, and it's resulted in fires which have resulted in loss of life and serious injuries. So internal combustion engines are definitely a source of combustion that have to be taken into account. And when we have a LNG bunkering operation, now say we're in a terminal that's basically a container port where the routine is to have vehicles passing by all the time, and nobody much gives it a second thought. When we're having an LNG bunkering transfer operation, with the possibility always exists, leak, vapor. So it's critical that we ascertain what our safety zone is, what our security zones are going to be, and that those zones are strictly enforced, and that we don't allow vehicles, pickup trucks, anything else of that nature into that area during the transfer process. So something to bear in mind, particularly if you're part of the port authority or terminal authority and are going to be looking at LNG bunker transfer in the future if you're not already doing them. The fire will continue to burn until the hydrocarbon is depleted. Usually they're relatively short in duration, and once again, unconfined vapor doesn't get the flash fire effect, but there will not be an explosion. Oftentimes, we'll be looking at firefighting procedures a little bit later on today, uh, and one of the methods of actually firefighting sometimes is to let the fire burn. Basically, you have a controlled burn. If you can't control the source of the fuel, sometimes it's safer to actually allow the fire to burn and cool down surfaces around it, in the vicinity of it, rather than putting the fire out. Put the fire out and you haven't secured the source of fuel, you now run the risk of reignition. You run the potential risk of vapors getting into confined spaces where you actually may wind up with a situation worse than you originally were confronted with. So each one of these incidents has to be taken on its own merits and looked at closely, and decisions have to be made exactly how we're going to approach it. The propagation of the flame is really relatively slow. It's not one of these situations where you have ignition and you have this flame that races back to the source. It's, you could, believe it or not, a human being can actually outrun a fire, a flame in a vapor cloud scenario. Uh, you don't have to be in the greatest shape in the world either to move faster than the flame. Uh, Obviously, if you got involved in one of these things, I'm pretty sure you'd run pretty darn fast. But the fact of the matter is that the propagation is relatively slow. It not it's not the sudden thing suddenly out of control. Flame height is going to be Flame height and flame direction is going to be wind dependent. So if you're in a position where do confront one of these fires, there's a high wind blowing in a particular direction. The height of the flame is going to be reduced because of the wind, but that flame is also going to be directed into the direction of, it's going to be the directions to which the wind is blowing. So height and direction are totally wind dependent. A vapor cloud fire may stabilize as continuing jet fire for pool fire from the leak origin. Basically, what happens here is you can initially start with a jet liquid. Uh, let's say there's a breach in a line that's under pressure that contains liquid, and the liquid coming out of that line under pressure jet. Uh, that liquid is, in all probability, if this is within the confines of a terminal operation, uh, you're going to have berms set up so that if you ever do have a situation where you have a liquid leak, find that liquid area. But initially, that liquid's going to be coming out under pressure, and liquid is going to pool inside the berm. So you could initially have a pool fire where the source of ignition meets at the outer edge of the pool, and that in turn will work its way back, and ultimately could actually work its way back to the source in this case, which is the liquid coming out of the pipe under pressure, and then you have what's called a jet fire, and that basically is it's fire under pressure, and the firefighting technique is a little bit different than that of a pool fire, and it's one of those scenarios that, in all probability, if you can't secure the source of the leak, you will allow to burn under controlled conditions if at all possible. You're not about to put this type of fire out until you secure the source. So again, as I did mention, each one of these incidents is going to be different, and has to be treated differently. It has to be fully assessed. You have to know exactly what you have before you approach a fire scenario and begin to fight the fire. Okay, a jet fire may be caused by vapor leaking from high pressure sources such as pumps, vent risers, piping of vent risers, uh, uh, a pipe coming up from the system. Uh, it would contain vapor, and sometimes this vapor can be under pressure. A good example of this, one of my first tours as an officer on board an LNG ship. We were transiting from Indonesia to Japan. We were on the edges of a typhoon. The ship had been doing an awful lot of rolling, pitching, and movement, and we had very, very high tank pressures. And we were at a point where we couldn't consume all the vapor that was being generated because of the bad weather. And as a means of relieving pressure in the tanks, the forward vent was opened up, and we relieved some of that methane into the atmosphere. And while this was occurring, it was either static electricity buildup due to the vapor rushing through this pipe, or it was a lightning strike. Either one. I'm not quite sure which one it was, but whatever it was, there was an ignition source, and the vapor coming out of the forward vent riser was ignited. And believe me, it produced a very, very impressive flame. Uh, the fire was extinguished by securing the source. In this particular case, they just closed the valve to the vent riser, and the fire was extinguished. So you can get a fire in this type of scenario. The vapor must meet an ignition source, and the vapor doesn't ignite spontaneously because the ignition is very, very high. You meet a source of ignition, you can have fire. Vapor will ignite again if it meets an ignition source. It's let's see, 1454. I'm going to call it stop right here, and Jared, if it's okay with you, we can take our break, and when we come back from the break, I'll answer your question, and we'll proceed with the remaining parts of this section in the next section. Okay. Yep, sounds good to me. 13:30 works well. Thank you very much. Or excuse me, 15:30. Yes, I saw that. An instant replay. Yeah, 15:30 works fine.